Hello everybody. So today we're going to be doing a problem with the diesel cycle, okay? This problem, and I'll put it in the description below, says that at the start of the compression stroke in a diesel cycle, the air is at 100 kilopascals and 27 degrees Celsius. The air is compressed until its pressure is 2 megapascals and the maximum cycle temperature is 837 degrees Celsius. What is the thermal efficiency of this cycle? Now, what we're always going to do, I'm going to go ahead and list what I know first. I'll do T2, I just don't want it to run into this right here. So I'll do T2 over here, T3, and T4. P2, P3, P4. Okay. So it says, now what might be useful is for us to draw out the graph for a diesel cycle. Y'all forgive me, I've not slept, it's almost like 12 p.m. I don't know, I haven't slept, I don't know, I didn't sleep last night, but, so just forgive me if my brain's working a little bit slow, okay? We'll start off with a PV diagram. Okay, so I know that the diesel cycle starts off with an isentropic compression, right? So it goes something like this, like this, like this, like this, right? Cool. This is what my diesel cycle looks like. Cool. Now let's do a TS diagram, okay? TS diagram looks something like this. Okay, now, I know that it starts off with an isentropic compression. So it says at the start of the compression stroke in a diesel cycle, the air is at 100 kilopascals and 27 degrees Celsius. 27 degrees Celsius is just 300 Kelvin, okay? Meaning that at the first state, at the start, it's at those values. So 100 kilopascals and 300 Kelvin. And I'm putting them in Kelvin because we're going to use some equations that require us to use Kelvin, so it's just easier for us to go ahead and do that. The air is compressed until its pressure is 2 megapascals, and the maximum cycle temperature is 837 degrees Celsius. I want to point out that the maximum, I'm so sorry, I did this totally incorrect. And the reason I know it's incorrect is because an isentropic compression, which is the first step, involves constant entropy, right? So I know that I actually have to be starting from here. This is my 2. This is my 3, this is my 4, okay? So, what I wanted to point out here was that, what did I want to point out? It says, so it's a compressed until its pressure is 2 megapascals, right? So the compression phase is just 1 to 2. So 2 megapascals is my P2, okay? Now, I know that my P2 is equal to my P3 just based off of that graph, right? Even it's a constant pressure heat addition, right? So P2 is the same as P3, so 2 megapascals, right? And the maximum cycle temperature has to be T3, right? I can see that off of my TS diagram. So T3 is 837 degrees Celsius, which is 1110 Kelvin, okay? Now, we can use some things that we call, I don't really know what they're called, but they're like the equations we can use for isentropic processes, for ideal gases, okay? So, the equation that I'm going to use, I have it written right here. Hopefully they give you an equation sheet. T2 over T1 is equal to P2 over P1 to the K minus 1 over K. And this K value is, I can't remember what the name, I think it's I can't remember what the name of it is, but basically it's just a ratio between like the specific heat at constant pressure and the specific heat at like constant volume, okay? So you can find it in your tables, like it'll be given to you. I don't think with a question like this, they won't really ask you to find it, okay? So this, using this, I can find my T2, okay? So I can say that T2, if I multiply both sides by T1, I can say that T2 is equal to T1 times this whole thing. Cool. So that being said, I can find T2. T2 is going to be equal to 300 times P2 over P1, which is 2,000, because this has to be in, you know, ratios, kilopascal to kilopascal over 100. So the K for air is 1.4, okay? And because it's an ideal gas, because it's the ideal Otto cycle, we're using cold air standard assumptions, meaning that we take, yes, it is a mixture of fuel and air, but we take everything to just be air, the ideal gas in this situation, okay? So once I punch this into a calculator, I get that T2 is equal to 706.06 Kelvin, okay? So I'm gonna go ahead and write that in there. T2 is equal to 706.06 K, okay? Cool. Now, I'm looking for P4 and T4. I'm looking for T4 actually, because so what we can realize about this whole thing is that it's a closed system. So we can apply our first law for closed systems, and I'll sort of show us how to do that later on. But I know that I'm gonna need T2, T3, and everything to sort of get my answers, okay? So what I'm gonna do is I'm gonna solve for all of the specific volumes here. And I know that my ideal gas equation says that P times specific volume is simply equal to R times T, right? That being said, my specific volume is equal to RT over P. So I can say that V1 is equal to RT1 over P1, V2 is equal to RT2 over P2, and V3 is equal to RT3 over P3. V4, I don't really have anything there yet, but we'll do something special there. R for air, again, you find this in the table, is equal to 0.287. T1 is equal to 300 Kelvin. P1 is equal to 100. R2, 0.287. Well, it's not really R2, it's just R. T2, 706.06. P2 is 2,000, because that's being kilopascals. 0.287, once again, because we're still dealing with air. 1,110. P3 is 2,000 kilopascals. So all of these get me and these are meters cubed per kilogram, okay? And you should be following along with me as I'm doing this, I can make mistakes, even though, like, hopefully I'll double check it before I upload this video, but, you know, I might be having one of those days. I haven't slept. Cool. So I'm gonna go ahead and write the V1 equals V2 equals V3 equals V4. I don't have. However, I know that V4 is equal to V1, because it's a constant volume. Oh no. Wow. I think this was 0.861. That was 100, and this was 300. Yeah. Okay. So we have this, right? Cool. I know that my V1 is equal to my V4 because of this graph right here. And it also tells us that it's a constant volume heat rejection, right? So V4 is equal to 0.861 meters cubed per kg. And what I want you to realize is that those equations that I told you about before for the isentropic processes also say that when I say T2 and T1, I simply mean the final point and the initial point with an isentropic process. So I can likewise say V3 and V4 when comparing them, right? So T4 over T3 is equal to V3 over V4 to the K minus 1, okay? Now, T4 is simply equal to T3 times all of this. T3 is equal to 1,110 times V3 over V4 K is still 1.4, and with this we get that T4 is equal to 565.13, and that's going to be in Kelvin. Now, we basically have everything that we need to, or almost everything that we need to solve our problem. So I know that I have an isentropic compression, right? Then I know that I have constant volume heat addition, isentropic expansion, and constant volume heat rejection, right? So I know where my Q in and Q out are coming from, right? Really, all I have to find is Q in and Q out. You could go ahead and find work net, but it's a lot easier. I mean, yes, like it's work net over Q in to get the thermal efficiency, but I feel like that's gonna be a whole lot more work. So just sort of trust me on this, okay? Let's see. Now I know that Q in is from point 2 to point 3, right? So I'm gonna go ahead and look at that in a closed system. And I'm gonna go ahead and say that Q minus W, I'll just say for 2 to 3, Q minus W equals delta U. And I do have the equations right here, but I'm just trying to show you where these equations came from, okay? Now, we're looking for Q, right? So Q is equal to W plus delta U, okay? Now, what can we say about this? I know that P dV is equal to my work. I know that, so there is a change in volume. I know that constant volume heat addition. Constant volume would tell us that this is CV. I'm sorry, this is constant pressure, so this is CP, okay? So this is a constant pressure. This becomes this has to be higher than this. This work goes to 0 because there's no work being done when like heat is being added, if that makes sense. There's no work from the constant pressure heat addition, okay? And let me just double check myself on that. So yeah, so this should be CP. Yes. There's no work when this is happening. So I can go ahead and cancel this out. So I don't have to worry about adding. Yes, it is W plus delta U, but delta U doesn't apply. I mean, W doesn't apply here because there's no work being done. Okay. That being said, I also need. I know that there's Q out from point 4 to point 1, so that's constant volume. So same thing. 4 to 1. Q minus W equals delta U. No work. Q is equal to CV because constant volume. And I'm just gonna do whatever temperature is higher in all honesty. So it's gonna be T4 minus T1 because we always want a positive number, right? And that's the same thing I did here. T3 minus T2. T3 was the higher number, T2 was the lower number, even though it's also like final minus initial, right? So, so my Q, and probably what I should go ahead and do is honestly make these lower cases. These should low-key be lower cases, high-key. I'll just go ahead and rewrite it like this. Qin is equal to Cp T3 minus T2. Q out is equal to CV T4 minus T1. Cool. CV for air is 0.718. Let me double check myself. I didn't write it down. When you want to find the CV for air, you can go into your there's a table, hopefully a table booklet will be provided for you. I wouldn't expect you to memorize everything. But CP for air and CV can be found here. CV is 0.718. T4 is 565.13 minus 300. CP is 1.005. T3 is 1110 minus 706.06. That gives my Q in is 405.96, and that's kilojoules per kilogram. This becomes 190.36 kilojoules per kilogram. Now, I know that eta is given by 1 minus Q out over Q in, and that gives me 1 minus Q out, which is 190.36 over 405.96, and that gives me 0.5311. So your eta, which is what they asked for, the thermal efficiency, is 0.5311 or 53.11%. This is your eta. I don't know if eta can be given as 53.11, but the thermal efficiency is 53.11%. So this is your final answer. And I mean, everything, you can sort of do this intuitively. We use cold air standard assumptions. Is there anything I didn't talk about? The system is obviously an engine with the diesel cycle engine with containing air. Just everything that we've gone over. We use the normal equations that we know we needed to use. I didn't even have to memorize these. Like, yeah, you can sort of memorize them at a point in time once you use them enough. But you can sort of intuitively figure these out, right? Constant pressure, constant volume. Constant pressure, constant volume, right? We know that heat is going in one, heat is coming out in the other. Again, if I didn't make anything clear, please feel free to ask questions in the comment section. Don't forget to like and subscribe, and please always read the descriptions in the videos that I have. Sometimes if I ever make mistakes, I put corrections in there. So let's keep learning thermal. Thank you.